So today we're going to talk about something called significant figures. Okay, some people call them significant digits. So you'll hear people call them SigDigs, but I call them SigFigs. Okay, significant figures. What a significant figure means is it tells us kind of what digits of a specific measurement are valuable, what we really care about. Okay? So not every single digit you might read out of a measurement is considered significant. Okay, not all figures, not all digits in a measurement might be significant. All right, so today we're going to learn some rules to determine which digits or which figures in a measurement are considered significant. Okay, so let's take a look at an example here. Okay, I have a measurement that has what I consider 3 significant figures. I've measured 2 digits. I've estimated 1 digit. Okay, so whenever you take a measurement, you read what your instrument gives you, and you estimate 1 more. Okay, so this particular measurement has 3 valid digits. I've read that it was 14 centimeters at least, and I estimated that it was about 0.3 centimeters longer. Okay, you read what your measurement gives you, you read what your instrument gives you, then estimate the last digit. So go ahead and put that into your notes too. When you're taking a measurement, you read what your instrument gives you and estimate 1 more digit. Okay, so let's just take a look at this little ruler or whatever I've drawn up here. Okay, I have a 38 centimeter mark and a 39 centimeter mark. Can we see that correctly? So if these are centimeter markings, our big ones, what do these little tiny marks must have to be? Millimeters. They have to be millimeters, right? And our ruler is marked to millimeters. Okay, so if I have a measurement that I think is located about here, okay, can we see that where that arrow is located? Okay, I'm going to measure what my instrument gives me, and I estimate 1 more digit. So that means I'm at 38.123 centimeters. That's me reading the instrument, 38.3 centimeters. And where do we think this falls in between that 0.3 and 0.4? Yeah, it falls almost exactly in the middle. So this measurement would be 38.35 centimeters. All right, I read what my instrument gave me with these first 3 digits. These were given. This last one was estimated. Okay? Yeah. So our rules for SigFigs. Any digit that's not a 0, so any non-zero digit is always significant. Whether it comes first, last, in the middle, wherever it goes, it's always significant. So the only questions that we really start to have about significant figures involve zeros. Okay, so anything that is not a 0 is always significant. Zeros to the right of digits after a decimal point are significant, and that is with the example that we just showed. Zeros to the right of digits after the decimal point are significant. So this measurement right here that says 8 centimeters, that's saying that we think it has around 8 centimeters. That's my guess. That's my measurement, my estimate. I think it's around 8 centimeters. It has how many significant figures does this have right here?
2.
This one right here? 1. So 1 SigFig. This value right here has how many significant figures?
2.
It has 2. Okay, this digit is estimated, but it's telling us that I think it's exactly 8.0 centimeters. Okay? So that 0 to the right of digits after the decimal point is significant. Okay? Next rule is all zeros between digits are significant. Any 0 between digits is significant. So that might look like this. Okay, so raise your hand if you can tell me how many significant figures I have here. Yeah, Alexis, what do you think?
5.
5. Perfect. I have 1, 2, 3, 4, 5. These two zeros because they are to the right of the decimal point after digits. This 0 because it's in between non-zero digits. Okay? Questions so far? All right. Zeros to the left of digits are non-significant. So zeros to the left of digits before the digits start are non-significant. They become placeholders for our decimal point. Okay, so zeros to the left of digits before the digits start, not in between digits. Okay, zeros to the left are non-significant. Okay, they are simply placeholders. So this number right here, if you can't quite read it, is 0.0860. Okay, that's the example that's given up on the board. The correct number of significant figures is 3. 1, 2, 3, right here. These zeros are to the left of digits, okay, whether they are before or after the decimal point. Zeros to the right of digits after the decimal point. So if they're after the decimal point, they have to be to the right of digits in order to be significant. Okay? Does that clear that up a little bit? Okay, so these zeros are to the left of digits before they start, so they're non-significant. Okay? All they're doing is being a placeholder is what we call them. All right, so we only have 3 SigFigs here. And last but not least, any digit used in scientific notation is significant. And I want to make a clarification about this rule. So after you get it written down, just hang on for a second, and I want to make a clarification here. Okay, so scientific notation. Let's just do a quick review. So if I have the number... If I have this number, 2048.12, how do I put that into scientific notation? Okay, so I moved it to the left 3 spaces, but it's going to end up as 2.04812 times 10 to the what? Third, the positive third. Why is it not negative third? Because we moved it left. Yeah, when we expand it, we're going to move it to the right, which means our exponent should be positive. Anytime our original number, this number right here, is larger than 10, our exponent should be positive. Anytime it's smaller than 1, it should be negative. Okay, so that original number that we're trying to express, if that number is over 10, that exponent needs to be positive. Okay, so in our scientific notation, we're looking at every single number as being significant. So 1, 2, 3, 4, 5, 6 significant figures there. If I had shrunk this down even more and left it as 2.04 times 10 to the third, how many significant figures would I have? Only 3. Good. It's only the visible digits. It's not the expanded number that we're talking about here. Okay, so visible digits in scientific notation. So if I were to have 8 times 10 to the 9th, how many SigFigs would I have? 1. 1 SigFig. We don't expand that out times 10 to the 9th and then tell me how many significant figures that is. We look at just what its face value is. Okay? 1 SigFig. Questions there? Okay. Okay, the numbers that we aren't sure how many significant figures they have are considered ambiguous. Okay, that's what That's a word you need to be familiar with, okay? So if you're not sure how many significant figures a number has, it's considered ambiguous. And there's some rules for what is considered an ambiguous number and what's not, okay? Okay, so this is an example of an ambiguous number, and I'm going to tell you why it's ambiguous before we start looking at how we fix it. Ambiguous numbers have what I call trailing zeros. Okay, these zeros have no decimal point. They're not in scientific notation. You don't know if they're saying this is around 120,000. Is it 120,000.000? Is it a really, really exact value? Is it 119,900? Is it close? Is it not? You don't know. Okay, so any number that has trailing zeros with no decimal point is considered ambiguous. So those zeros right there are what we're talking about. They're zeros to the right of digits, but they're not after a decimal point. They're not to the left of digits, so they might be significant, they might not. That's what we're talking about when we talk about ambiguous numbers. They have trailing zeros with no decimal point. Okay? So this is what I mean when I say a trailing zero. These zeros out here are to the right of digits, but they don't have a decimal point, so we're not quite sure. Okay, so other ambiguous numbers would be 10, 80, 800, 8,000, whatever. You can keep going, okay? Anything with trailing zeros at the end would be an ambiguous number. But there are ways we can fix ambiguous numbers, okay? If we look at this number right here, 120,000, we could have two significant figures. If we just look at our non-zero digits, we could have 6 if we use all of our zeros. There could be 8 if you add 2 decimal points. There could be 9 if you had 3 decimal points. There's lots of different ways you can fix this, okay? So this is why we're not quite sure, because of those zeros. So here's our 2 rules to fix ambiguous numbers, because we don't like ambiguous numbers. I don't like for you to give me an ambiguous number as an answer to a problem. Okay, so there's 2 ways you can fix ambiguous numbers. Either by using scientific notation or by adding a decimal point. Okay. We can either add a decimal point or put it in scientific notation to correct our ambiguous numbers, if I wanted to. So if I put it in scientific notation, I could make 2 SigFigs here. If I put 1.20 times 10 to the 5th, how many SigFigs would I have?
3.
Yeah. So scientific notation gives you the most flexibility in terms of number of significant figures, because you can put as many digits after that as you want. Okay, you can make that as exact as you want. Okay? Scientific notation gives you the most freedom. Adding a decimal place automatically ensures that you're adding another, at least 1 0 to the end of it, if not as many as you need. Okay? But you can't, this doesn't work. 120,000 and then the decimal point to have 6 significant figures, that doesn't work. Okay? Because the decimal point automatically would tell us that there's a 0 following that. Does that make sense? So you can't add a decimal point without adding a 0, which would then add a significant figure. Okay? And why does this become significant? Why does adding the decimal place and adding the 0 here make this digit significant? Yeah, Garrett?
Tells you it's exactly 120,000.
And it's to the right of the decimal point, and it's after digits. So it follows our rules. So this number becoming significant makes all these other zeros significant. Okay, so here we would have 7 SigFigs. We're on the same page? Okay. Here's our math rules now. This is where it gets interesting. Okay, we have certain rules that we have to follow when performing math operations, interpreting significant figures, interpreting measurements. Okay? So whenever we're performing math operations, we've got to consider the number of significant figures so that we can give our answer in the correct number of significant figures. Okay? So let's talk. There's 2 different rules we follow. One rule for adding and subtracting, one rule for multiplying and dividing. Okay? So we'll talk about adding and subtracting first. So using significant figures doesn't ever change the way you perform the math operation. It doesn't change the way you add or subtract. It doesn't change the way you multiply or divide. It changes how you round your answer at the end. That's the only thing that it will change. Okay, so when we're adding and subtracting, we do the math just like normal. Then we round our answer to the least precise value involved. And what this means is that you round to the fewest number of decimal places. Okay, fewest number of decimal places given. So you need to start making this connection. When you add and subtract, you're looking at decimal places. When you add and subtract, you're looking at number of decimal places. Will have to correspond there with your final answer. And this can make some people pretty uncomfortable. Okay, it makes me pretty uncomfortable to sometimes have to leave my answer in whole numbers when I think there should be decimal places. But that's how it goes. Okay, so let's go ahead and try one here. Okay, you can assume that I did the math correctly here. Hopefully I did. But 12.520 plus 14.0 gives us this value. According to our math rules, according to our adding and subtracting rules, do we have the correct number of significant figures here? No. How many decimal places should our final answer have? 1. It should have 1. So we're looking at 26.5. Does this 2 round our 5 up at all? No. So you have to look at that next value too to see if it would round it up or down. Okay? So our answer there should just be 26.5. So it's not as exact as we would like it, as the math tells us, because we're dropping those 2 digits. But since one of our measurements was less precise, this value was less precise, our answer can be no more precise than our original measurements. Does that make sense? Yeah? Kinda? Okay. Let's look at our multiplying and dividing rules. So our multiplying and dividing rules. Again, the math operations don't change. You still multiply like you're supposed to. You still divide like you're supposed to. You round your answer at the end to the fewest number of significant figures. So round your answer to the same number of SigFigs as the least precise. So round your answer to the fewest number of SigFigs. Okay, a little plainer terms there. So after the math is done, you take a look back at your original values, see which of those has the fewest number of significant figures, and round your answer to that many significant figures. Okay? Yeah, you might have to condense it, you might have to put it in scientific notation, you might have to round some numbers. You have to take a look, but we're gonna try some practice ones of them here. Okay? So adding and subtracting, you're looking at decimal places. Multiplying and dividing, you're looking at number of significant figures. Okay? All right. So here I've taken 2.40 times 12. times 12. So if I'm looking at the number of significant figures, how many SigFigs does this value have? 3. Good. All 3 of those are significant. And this value has how many? 2. Why is this number not ambiguous? No trailing zeros. Okay? It doesn't have a decimal place, which is fine. No trailing zeros, and we know all non-zero digits are significant. So it's not ambiguous. Okay? So that means our answer needs to have how many significant figures? It needs to have 2. So how do we get this value right here to only have 2 significant figures? Round it to 29. 29. There's one other way we could present our answer here. What might it be? Good. 2.9 times 10 to the first. Okay. This also has two significant figures. So you could present that in scientific notation if you wanted to. Okay? All right, let's try some practice. Go ahead and do these two problems on your own, and then we're going to discuss our answers here. Let me have the raw answer for number 1 for our first problem here. Yeah, Trevor, what'd you have?
319.7.
Okay. 319.7. Okay, and someone tell me how many significant figures that value should have. Emily said 2. Why should we only have 2 significant figures in our answer? Emily, what do you think? Exactly. 2.3, one of our initial values, only has 2 significant figures. Very good. So if we only need our answer to have 2 SigFigs, can we round that down or up to 2 SigFigs? No. What if we rounded like this, 320? What's that give us? What's this number right here? It's ambiguous, which will get you a big frowny face. Okay? Don't give me ambiguous numbers. So, how do I fix that? Scientific notation. So, Grant, tell me what you had for your final answer.
3.2 times 10 to the second.
Times 10 to the second. Very good. And we're still missing one thing? Centimeters squared. Centimeters squared, because we took centimeters times centimeters, so our units should be centimeters squared. All right, our final answer has 2 significant figures. That's what we should have had based on this right here. Very good. Questions on that one? Okay, let's have a raw answer for the second problem. Yeah, Brayden.
26.281.
281, okay. Can someone tell me how many decimal places our final answer should have? Jenna says 1. Why 1, Jenna?
Because your least amount in the original problem is 1.
Good. We've got 1 decimal place here and 1 decimal place here. So our final answer is only allowed to have 1 decimal place, which means our final answer should be 0.3. Good. That 8 rounds the 2 up to a 3. Okay, so 26.3. And our units are just centimeters since we added, not subtracted. So you see that using significant figures can give you a less precise answer, a less exact answer than this. Here we had 3 decimal places, here we only had 1, but that's what our measurements called for. Okay, our answer can only be as precise as our measurements. So that's why we've got to use SigFigs. We good? Okay, let's move on to so scientific notation is always written in the form m times 10 to the n. M, this number right here, has to be between 1 and 10. Must be between 1 and 10. That's really, really important. Scientific notation, that value must be between 1 and 10. Quickly about the purpose of scientific notation. Can anyone tell me why we bother using scientific notation? What does it give us yeah, Grant?
For like large numbers and really small numbers, it's a lot easier than writing the whole thing out.
Exactly. Okay, scientific notation gives us a way to express really, really large numbers and really, really small numbers. Okay? So, what if I have a number like this? 38.42184. Really big number, really small number? Not really either of those. It just has a lot of decimal places. Okay, so how do I express this number in scientific notation? If I just want, let's say, 2 decimal places. What is it? 3.84 times 10 to the what? First. Times 10 to the first. I don't care about all these decimal places. Okay? I'm not moving to cover all those decimal places. I'm moving from 3.8 to 38. That's it. Okay? So we're not expressing a really, really big number here. We're expressing 38. If I had given you a scientific notation that looked like this, 3.84 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, that would have been a huge number. That's not expressing 38.428184. That's expressing, 38 trillion or something. Okay? Do we understand the difference between that? You need to make sure that if there's a lot of decimal places, that's fine. You might just have to chop those off. Those are not part of the number you're trying to express. Make sense? All right, good. Because I'm just freedom or gives us some flexibility when we need to express things in certain number of significant figures. You can chop those decimal places off. You can carry them out as long as you need to. Scientific notation gives you great flexibility when needing to express a number in certain significant figures. Okay? So let's say that I needed to express that specific value with 3 SigFigs. Tell me what my number would be. Now I'll give you just a second to finish getting it written down.
Times 10 to the 5th power.
Okay, 1.24 times 10 to the 5th. Do we agree? Good. Because we want to express this number, 124,215, a pretty large number. This number is larger than 10, which means our exponent on scientific notation should be positive. We're going to start at the decimal place here. 1, 2, 3, 4, 5 to express our overall number. We wanted 3 SigFigs, and we have 3 SigFigs in scientific notation. Yeah? All right, very good. Let's look at math with scientific notation. Have you learned rules for math with scientific notation? Maybe? Okay. So when we want to do math with numbers in scientific notation, there's certain rules you have to follow dealing with the exponents, dealing with things like that. So when we want to add and subtract numbers in scientific notation, we've got to make sure that n is the same. So we've got to make sure the exponent is the same for both of those. Okay, so if we want to add and subtract numbers in scientific notation, we have to make sure that the exponent is the same for both of those values. And we can adjust our number, our m value, outside of the 1 or 10 range in order to complete this. Okay, this is the only time that we can adjust that m outside of the 1 and the 10 range. Okay, is if we need to add and subtract using a scientific notation. Okay, we can adjust numbers. That means we can adjust the m value, right? The blank blank times 10 to the whatever. We can adjust this value right here outside of 1 or 10 if we need to make n the same. Okay? Okay, so let's look at how we would need to adjust these. Go ahead and get this one written down, and we're going to talk through about how we adjust, what we need to look at in order to change this to get those n values or get those exponents the same. Because right now they're different. So let's pick, would we rather have the exponent as the 3 or as the 4? You can pick.
3.
Okay, I heard 3 first. So if I want both my exponents to be to the third power, I'm going to leave this one as it is, 4.14 times 10 to the third. And I'm going to adjust this value to make it times 10 to the third. Okay? Can we see what that would look like? Can you see that right off the bat, or do we need to expand it out? Let's go ahead and expand it so that we can just see. So 1.23 times 10 to the fourth, if I expand that number, looks like this. 12,300. I just expanded it so we can see what it looks like. Now I need this number to be times 10 to the third. So I take it and I go 1, 2, 3, which gives me 12.3 times 10 to the third. Only time it would be acceptable to have a number in this spot right here outside of 1 and 10 would be to adjust it to add or subtract. Okay, that's the only time it works. So now both of our exponents are to the third power. We'll take 12.3 times 10 to the third. And we'll do our addition. Okay, so now what do we need to do? Our answer we've got to fix back. We cannot have our answer being over or outside that 1 and 10 range. Okay, so it should be 10 to the what? 1.64 times 10 to the fourth. All right, what questions do we have here? Can we see the transition between this number and this number? Okay, any questions on that? Because that can be a little tricky. If you have problems, if you're not seeing it, just expand the number and then put it in the correct form of scientific notation. Okay? All right, let's talk about multiplication now. When we multiply two numbers, this one's the easiest rule of all. When you multiply two numbers in scientific notation, you multiply the numbers like normal, then add the exponents. That's it. Multiply the numbers, then add the exponents. Okay, n, that's our exponent. That's what we're talking about, right? Because it was m times 10, to the n power. So n is always the exponent. So multiply the numbers, add the exponents. Have we heard these rules before? Maybe? Yeah? Okay, good. All right, so let's try this one. Yeah, good question. All right, so our raw number at the end was 32.4783, right? Do we agree with that one? Times 10 to the third, right? 5 plus negative 2 is positive 3. However, Amanda asked a good question. We've got to follow our significant figures rules. Okay? So if we multiplied, this number has how many sig figs? 3, and this one has, which means our answer can only have 3. So first of all, we've got to put this number in our correct form of scientific notation. So it should be 3.25. Rounds that up. Okay, and it's times 10 to the fourth. Okay, because we really need to move it one more decimal place. 10 to the fourth. Division of scientific notation. Divide m as needed and then subtract the denominator from the numerator exponent. So for this, we'll divide these two numbers, 5.44 divided by 8.1. And that gives us 0.6716 times 10 to the, yep, we're going to take 7, oops, I'm sorry. We're going to take 7 minus 4, and we get times 10 to the third. Yeah, so the units would be grams per mole. Yep. Grams over moles. So units here were grams, units here were moles. Okay, so there's our raw answer, but is our M value between 1 and 10? No. So we need to move that decimal place, which means our final answer should be 6.72. Good. And why are we rounding that 1/6 up to a 2? Only have 3 SigFigs here, but how many does this have? 2. So that means our answer should really only have, they should really only have 2 significant figures in our answer. Okay? And let's look at our scientific notation here. What should scientific notation be? 10 to the second. So if we look at this value, this number right here, 0.6716 times 10 to the third, if you take that and move it 1, 2, 3 places, that gives us 671.6. So about 670, right? And that's what we're saying here. If we move this 2 places, we get about 670. We on the same page? Okay, so here we can only have 2 SigFigs because 8.1 only had 2 SigFigs. This was our final answer. Units were grams per mole. And accuracy. All right, so if I'm talking about something that is precise, if I'm telling you that I have precise measurements, does anyone know what I'm talking about? Precise means what? Means they're close together, okay, or the degree of exactness of a measurement. Precise measurements mean that all of your measurements from all your trials are really, really close together. Okay, they have very little variance within your numbers. Okay, precision is how close together your measurements are. Accuracy tells us how close they are to the actual. How well your results agree with the actual measurement. That's your trick for remembering that. Accuracy is close to actual. Precise is how close together they are. If we want to have really great measurements, we need them to be both accurate and precise. Okay, we want them really close together, and we want them really close to the actual value. That would be ideal, right? But most of the time, we'll have an error in one or the other. Sometimes we can have precise measurements, but not accurate measurements. And sometimes we can have accurate measurements, but not precise measurements. Reading an instrument, that would give you which of the two? Would it give you precision or would it give you accuracy? Precision. If you are incorrectly reading an instrument, but you're doing it the same every single time, that means you might have really precise measurements. They might be really close together, but they're not close to the actual value because you're reading the instrument wrong. Okay? So incorrect but consistent reading of an instrument can give you precision, but not accuracy. Okay, so you would have precision, but you would not have accuracy. Okay, if you, within an experiment, have different people reading an instrument throughout the set of trials, you're going to have some errors maybe in both precision and inaccuracy. Because I might read the instrument different than Cece does. She's a lot taller than I am, right? So we might see it at different levels. I might just have worse vision than her or something like that. We've got to have the same person reading it. That way you have the same set of eyes on an experiment the whole time, okay? If you have different people that read your instruments, you could have really inconsistent, which means you could have really unprecise measurements, but you might not be accurate either. Okay, so different people reading instruments is one. Could have one accurate one that you find, but your other sets would not be accurate. So if you have one accurate measurement, but your average isn't accurate, that doesn't give you a good sense of accuracy. Okay, but you could have one accurate measurement, but if they're not close to that, they won't be precise. Okay, so that's how you can have one but not the other. For each of these values, they gave their variance numbers. That's what we mean plus or minus. That's telling us it varied plus or minus 8 centimeters either way. Paul's varied plus or minus 4 centimeters per second squared each way. So his values were somewhere between 938 and 946. That's what he's telling us. His average overall was 942, but he had very little variance, which means he has the most precise. Okay, so Paul was most precise. Ronald had the most accurate average value at 961. Okay, he had the most variance, but his average was closest to the accurate or the actual value, which means he was the most accurate. Okay, that's what the plus or minus means. That's their variance levels within their measurements. Okay, makes sense? All right, last thing for today is density. So let's get through density. Have you dealt with density before? Most of you knew the equation right off the bat. So density's equation is what? Mass over volume. Good. Density is an intensive property of matter. So what do we know about intensive properties?
It don't matter how much of a substance there is.
Perfect. Doesn't matter how much of a substance it is. Density is the same regardless of the size or the amount of substance that you have. Density is a specific intensive chemical property. Okay, each specific substance has its own specific density. So density is an intensive chemical property. Density equals M over V, mass over volume. I think that's an equation you've probably heard before. Density equals mass over volume. Most of you knew it on your pretest, which is good. Density essentially shows us how compact matter is. Okay, I know that's probably not the scientific term or anything like that, but that's essentially what density is, and density is difficult to describe, so this is the best way I can think of to describe it. Okay, it tells us how compact the matter is. If something has a high density or something's very dense, those atoms are close together. There's not much air between each atom. They're very close together. Okay? If something is not very dense, atoms are farther apart. They have some more space, some more room to breathe. That's basically how we're looking at density. Okay? Does anyone know what the density of water is? Yeah, what is it? 1 gram per milliliter. 1 gram per milliliter. So the density of water gives us a good clue as to the density of other substances, whether it sinks or floats in water. Okay? If it sinks, that means it must have a higher density. There's less air particles floating around in those atoms. If it floats in water, that means that it must not be very dense, which means it has some more room to breathe. Okay? So I know that compact probably isn't the right word, but that's the best way I can think of to help you visualize and describe what density really means. Okay, how close together, how compact those atoms are. All right, so let's try some practice ones here. Yeah, I'm sorry, Alexis. I'll go back. You need your calculator out. If you haven't already put it away, you still need it. All right, let's see here. We're going to find the density of an object that weighs 16 grams and has a volume of 0.35 centimeters cubed. Sorry. Mass over volume. Centimeters cubed is a volume unit, believe it or not, right? Because centimeters cubed means we took length times width times height, which gives us a volume. Let's make sure we're taking a look at our significant figures when we're calculating our final answer here. So mass is equal to 16 grams. Volume is 0.35 centimeters cubed, or cubic centimeters. All right. Our raw answer, I had a raw answer of 45.71 grams per centimeters cubed. Does that have the correct number of SigFigs? No. What should our final answer be with the correct number of significant figures? Our answer is going to be 2? Our answer should have 2 SigFigs, which means we're going to round up to 46 grams per centimeters cubed. All right, do we agree here? Okay, do you know that a centimeter cubed is the same as 1 milliliter? Yeah?
No.
Centimeters cubed unit, that volume unit, 1 centimeter cubed is the same as 1 milliliter. Okay, so if you ever see those units for density, they are interchangeable. Okay? And have you ever heard doctors say, I need so much cc's of something? I need 50 cc's? Cc's means cubic centimeters. So essentially they're saying I need 50 milliliters of something. Okay? Cc's and cubic centimeters and milliliters, they all mean the same thing. Okay? Just that's your, fun fact of the day. Okay. Certain compound has a density of 3.21 grams per mil. If I have 24.8 grams of the substance, what's its volume? D equals M over V. I have density given to me. Grams per milliliter. My mass is in grams, so I don't have to do any unit conversions, which is handy. 24.8 grams over my volume. Solving for this bottom variable, do we know a shortcut? Has anyone showed you this? If I have a bottom variable I'm solving for here, I switch these 2 places. So that would leave me with V equals 24.8 grams over 3.21 grams per milliliter. Okay, and the reason that works is because I would be getting rid of V here, moving it to the other side, and then I would divide by the 3.21 to move it to the other side to get V by itself. Okay, so that's just a little quicker way to look at that if you have a system that looks like this and your variable's on the bottom. All right, Cece, what do you got? Oh, you didn't get the raw number. Okay, tell me what your final answer with SigFigs is. 7.73. And what are units? Perfect. Do we agree here with our SigFigs even? Yeah? How do we know that our units will come out in milliliters? Yeah, that's what our density unit was, grams per milliliter. So these units all have to match. Our volume unit, our mass unit, and our density units, they need to match. Okay, otherwise we're in big trouble. They've got to match. Okay, last one. I want you to do this one on your own.